Hi, my name is Preston Culbertson. I'm in lab section MO6, and today I'm going to be going over lab 5, which is the motion of falling objects. My main objective of this lab was to explore the effects of gravity and air resistance on falling objects of two different masses. And my main results of this lab was that 1, air resistance is needed to create a proper model of falling objects, and especially if you disregard air resistance on those with small masses or large areas, you're going to have a very inaccurate model. And 2, falling objects reach a terminal velocity where air resistance will cancel out the force of gravity on an object. So my main experiment this week was that I took a video of two different objects of two different masses falling. One was a heavier object, which was a book, and the other was a lighter object, which is a newspaper. And so I used this program called Tracker to take physics data of both of these videos. The first, I used a calibration stick of a poster in my dorm room to accurately measure the distance, like to set the real world distance in this video. And then I had my roommate drop the paper, and I measured using point masses the center of mass as the object fell. The second, similarly, I had my friend Kara drop a book in her hallway, and so I used the calibration stick to measure what the real life distance of this spine of the book is. And then I also set up in both videos the origin to be at the center of mass of the initial starting position of the falling object. And so as you can see, as the book drops, the point masses, which I entered in manually, follow it. So I took that data and put it into Excel, and I'll use it later to compare to my computer model, which I'm going to explain right now. So my computer model, I used VPython to set up a model of the systems. I entered both of the masses of both of the objects into VPython, along with some other initial conditions such as its starting position and velocity, which were both 0 as they were dropped from rest. And then I also set the time step to be 1/30th of a second, which is exactly the same as what Tracker uses. We used iterative calculation in our simulation this week, which essentially is a update of at each point, at each time step, we do the calculations over and over again, and this gives us an accurate model to continue to predict the system's motion. And so there were two forces acting on the objects this week. One was the gravitational force, which was down, so we just entered, it was a vector 0 in the x direction, the mass times the gravitational constant in the y direction, and a 0. And then also we used a drag force, which is, we used viscous drag, which is merely proportional to the velocity of the ball. So it was a constant of proportionality, which we found using experimental data, times the velocity. So now I'm going to go to my data. The first object is the heavy object as it fell. And here we can see the model with drag is in red, the model without drag is in blue, and the experimental data is in green. And so as you can see, the experimental data is a little squiggly, and that's because of a couple reasons. One is that we may not have factored in enough forces. There are different types of air resistance that may have acted on the object. And B, there's some human error. This model comes from, or this experimental data comes from Tracker, and so I may not have been super precise in my clicking, and so that may be what causes the curve to be a little squiggly, but it still follows the general trend of a falling object. And so as you can see, the model with drag is a little bit more precise. It ends at the correct position compared to the model without drag. But for this heavy object, we can see there's not a huge difference between the model with drag and without drag compared to the experimental data. However, on the light object, we can see a huge difference. Here, the experimental data is in blue. The model with drag is in green, and the model with no drag is in red. And so we can see the model with no drag far underpredicts where the position of the object is going to be over time. And so the reason for that is that the model with no drag predicts how the object would fall in a vacuum. And so for this light object with a light mass and with a large surface area, the force of air resistance is actually pretty big. And so to have an accurate model of its motion as it falls downward, we must include air resistance. Now I'm going to go over to my what does it mean question, and that is, for an object that drops slowly, which model predicts a terminal velocity? So a terminal velocity, just to start off with, a terminal velocity is a constant velocity while falling, and this happens when F net equals 0. And so the model that's going to predict that terminal velocity is the one that factors in drag. Here I've plotted the velocities of objects falling, or of the falling lighter object. And so as you can see, the red line, which is without drag, predicts that the velocity is going to continue decreasing over time, whereas the model in blue that does include drag predicts that the velocity is going to level out and become constant, which is when it reaches its terminal velocity. And so thus, the model with drag is the one that predicts the terminal velocity. I'm going to go to the what if question, which is what if the object was thrown downward initially instead of dropped from rest? And so I'm going to go to my data over here. And so I plotted both models with and without drag of objects being thrown downward. And so what we see here is that for the model without drag, it doesn't have much effect. It just means that the velocity starts at one lower, and then it continues to decrease at the same slope. And for the object with drag, we can see that that curve is actually leveled out a little bit. It starts at one lower, but it still reaches the same terminal velocity, which is slightly above -3 that we see here. And so actually I'm going to show on another chart the velocity, whether it's thrown downwards or whether it starts from rest. And so what we see is that they actually both approach that same terminal velocity value. And so the reason for that is that viscous air resistance is proportional to velocity, no matter what the initial velocity is. So the falling object still reaches the same terminal velocity, or the same velocity where air resistance balances force of gravity. So my name is Preston Culbertson. This is Lab 5, and thanks for watching. If you have any questions, leave them in the comments below.